It was PPT. What's that mean? Precipitate formation, yes. And anything else you guys can think of? Unexpected color change. So we've got all these chemical indicators now. Now we're going to see some today. We're actually going to do some chemical reactions, and next week you guys get to go by yourself. I'm just going to show you today. Okay. The only things I want to review here are basically the phases of matter: solid, liquid, and gas. Right? Elements that are simply from the periodic table. They have a particular state in which they exist. All metals usually are what? Solid, liquid, or gas? Solids. All nonmetals are usually gases. What's the one halogen that is not a gas at room temperature? There are two, actually. Bromine is liquid at room temperature. Iodine, it's a solid. It was that metallic-looking crystalline one I showed you, and I showed you how it reacted. It turns purple. So iodine's actually solid. So we can't assume everything, but we can assume most of them. All right. Aqueous. Aqueous is the last thing. This was on your equation writing. What does aqueous refer to? Right, dissolved in water. All right, cool. So let's look at equation writing. This is me making sure I'm covering all the bases. We all know reactants are on the left, yielding products on the right, yes? All right, common knowledge. The whole law of conservation of mass that we just talked about, where the mass of the reactants and the mass of the products are the same, the way that works is basically this one statement here. Atoms of reactants rearrange. As the atoms rearrange, the atoms are not going away. They're just taking on new partners, finding new friends to bond with. Maybe they go out by themselves and they're just singletons. They're just literally rearranging. So the rearrangement into products means that we're not destroying or creating anything, we're just rearranging them. So the rearrangement part is something we've spoken of before for the law of conservation of mass and matter, but that's kind of the basis of it. Even if you have heat forming, precipitates forming, gases forming, anything like that, any of those chemical indicators of evidences of chemical reactions, they can happen. We're still not losing mass, okay? Unless you just don't capture it because you didn't get a balloon. That's all right, though. Next page, thumbs up. There you go. All right, now balancing. All right, so this right here, your equation writing, you're going to tell me what the reactants are, what the products are, okay? So have your stuff in front of you. When solid zinc is added to a solution of copper 2 sulfate, aqueous zinc sulfate and precipitate of copper are formed. Josh, tell me the reactants. Like, give me and spell it out for him. Zn, solid, plus, keep going. Okay. Yields, solid. Jessica, pick up. Pippa. Pick up from there. He did reactants, you do products.
Oh, okay.
Solid? Yeah? Okay, cool. Good job. Next one. When solid magnesium chlorate is heated, solid magnesium chloride and gaseous oxygen is formed. Morgan, give me reactants. Parentheses 2, okay.
Solid.
Okay, oh, solid, thank you. Tyler, finish it up. Oh, what? Oh, somebody help him. O2. Diatomics. Don't forget your diatomics, and they exist by themselves. They have to have a buddy. So that's like the big 7 in hydrogen. So the big 7 includes, who's the first one on the part of the 7? Nitrogen. So that's N2 by itself, O2, F2, Cl2, Br2, I2. That's it. All right, so this is O2 gas. All right, good. Next. Like I said, fast and furious, because this is nomenclature. This is all it is, but we're adding a little bit more information to it. Aja, solid sulfur reacts with oxygen gas. Reactants. Gas. And then Chris, pick up. Gaseous sulfur trioxide.
SO3 gas.
Beautiful. All right, we're going to go through and balance these in a little bit, okay? So sulfur is just sulfur. It's not sulfur 2. It's not the S2. Solutions of silver nitrate and sodium bromide react to form. I'll stop there. Giselle, pick up. Silver nitrate. Plus.
Oh, AQ.
Thank you. AQ. Plus.
NABR.
Okay. Aqueous, right? Jamie. Form aqueous sodium nitrate and precipitate of silver bromide. So that's aqueous sodium nitrate. Okay. And then precipitate, you can denote it 2 ways. You can either put PPT underneath it there. I like to just literally say, we all know a precipitate is just a solid that's formed from 2 liquids, yes? So it falls to the bottom of the test tube, right? Because it's a solid. So I just draw an arrow down, because that means there's a solid dropping, yes.
Would you put it like under it like that? Or?
Yeah, just like I'm kind of putting like another subscript, that's all I'm doing. Or you can put PPT over there, yeah.
Could you put an X?
No. I mean, you could, but if I say precipitate, I want you to know that precipitates are solids formed from 2 liquids. A solid could just be a solid that's from a single replacement reaction. So there's a slight difference, but I'm okay with you being solid. All right, cool. Let's do the rest of these guys. All right, electricity. Oh, and I didn't do this on the decomposition one. Right here. Chloridase heated. What was the symbol in the equation writing worksheet that meant heated? Triangle, right? Okay. So you put a triangle above the yield symbol, and that tells me it's heated. You don't even have to say it. I know what triangle means. All right, same thing for when we get to electricity. When electricity is applied to liquid water, it decomposes into hydrogen gas and oxygen gas. Abby, give me the full thing, because actually it's liquid water. I got you on liquid water. Here we go. Liquid water. Okay. Give me hydrogen gas and oxygen gas. The symbols for them. H. Somebody? 2, because that's the diatomic, and O, 2, because it's one of the diatomics. Remember, the big 7 in hydrogen are all your diatomics. So when they exist all by their lonesome, they're not really by lone. They have a double. They have a mini-me. Okay, so that's gaseous and gaseous. And you can just put elect like that to tell me there's electricity applied there. All right. Mercury 2 oxide is heated to produce solid mercury and gaseous oxygen. Darian, give me what you got here. Give me the whole thing. Well, you can do it from here. Mercury 2 oxide. I'll do the first. Mercury 2 plus, oxide 2 minus. So if you go with it like that, you can see that the 2 and 2 will go crisscrossing, but then of course you would like to reduce the Hg2O2. Doesn't say the state. I'm going to go solid. Produces solid mercury and gaseous oxygen. You can do that from here. And what do you guys want to put above the arrow? Heat. Okay, good. Yeah. No, okay, so this is weird because when we crisscross, it goes Hg2O2. You reduce them down. Mercury actually has a weird timer stage. So if you did look this up at all, you could have seen, no, that would be mercury. That would be mercury. Nope, that has to be like that. Has to be like that. Okay. Last one. Oh, did I say liquid? No, it said solid. I don't know why I have a liquid there. Solid. Okay. Last one for now. Aqueous potassium iodide and aqueous lead 2 nitrate react. Erin, give me what you got here. Give me the reactants. Potassium iodide, aqueous, and Alexis, help him.
KiQ plus PB.
PB is lead 2 nitrate though.
Yeah,
NO3. Okay, and thank you, aqueous. Oops, I should have written this over to the side. So let me scooch this over. All right, Aaron, pick up from here. Yields producing solid lead 2 iodide. PB what? That's 2 plus that you're thinking. PB2, right? Lead 2 is a 2 plus for lead. You crisscross it over. So you're thinking PB2. And iodine is a what charge? Right, so crisscross. I2, solid, right? Okay. And potassium nitrate. Okay, NO3. Good job. Okay, aqueous. And do I have, oh no, do I have one more after this? I think I do. No, I do, but I'm going to go straight to balancing now. So what we have is we have all of our equations. If you have all of your equations, we can easily balance from here. So I'm going to do a couple with you, and then I'll let you guys do the rest by yourself, just to make sure that we remember balancing. So you guys did some of it in like 7th grade? Yeah? Yeah? Okay. So let's go back to the first one we did. Zinc, and I'm going to work with the ones I have written a little bit better here. Between all of these, what you want to do is you want to count up the individual subscripts of each element, and then see if it's balanced on either side. And if it's not balanced on either side, for balancing, all you can add, for balancing the equations, the only thing you can add are coefficients. That's it. No more subscripts added, because subscripts have already been applied, because you do your whole crisscrossing method to make sure that anything that had a subscript should have a subscript. So how many zincs on the left? Shout it out. Let's go. 1. How many zincs on this side? 1, because there's an imaginary 1 back there. Zinc is good. How many coppers on this side? 1, because there's an imaginary 1 right there. How many coppers on this side? 1. How many sulfates? And this is the trick. Do not break S and O apart. See how they stay together here? And see how they stay together here? Your life is so much easier if you just count how many sulfates you have, especially if it doesn't change from left to right. So how many sulfates are here? 1. How many sulfates are here? 1. Okay, everything's balanced. So the ratio of the coefficients are 1 to 1 to 1 to 1. That one was already balanced. Okay, so that was an easy one. Next one. How many magnesiums? 1. How many magnesiums? 1. How many chlorines? And I just go in order, okay? Just go right from left to right. How many chlorines are here?
2.
Right, because there's a 2 times a 1, so that's 2 chlorines. How many chlorines are here? 2. Okay, so we're in good shape. How many oxygens are here? 6, because 2 times 3 is 6. 6 oxygens, okay? So 6 oxygens. How many over here? 2. Now you are allowed to add a coefficient only. So what are you going to put in front of this? A 3. So that's just because you can't add anything else but coefficients. You needed 6. So the only way you can get 6 is 3 times 2. So the coefficients are 1 to 1 to 3. All right. Yeah. What's up?
I thought you said you couldn't break it apart.
What do you mean you couldn't break it apart?
Like with the
Oh, I said if it's left together. You can break it apart. This happens to be a decomposition reaction. So there's 5 types of reactions, right? It depends on the type of reaction as if it breaks apart the polyatomic. The first one we did is actually a single replacement reaction. It doesn't, the only thing that happens is zinc and copper switch places. Sulfate's just chilling. Okay, this one, chlorate, actually gets broken apart. So it depends on the type of reaction. Good question, because we're going to go over that in a second. All right, so this one, this guy right here, how many S's? 1. S's on this side? 1. How many O's on this side? 2. 3. Okay, so how do you balance 2 and 3? Tyler? What's a common, what could you multiply them both by? Or separately by? So just multiply them by their opposite, their other ones, right? So 2, the next, if you have 2 and 3, the next common multiple, I guess is what you'd say, is 6. Yeah? So you want to multiply this one by 3 and this one by 2. Because you want 6 oxygens here and 6 oxygens here. But guess what? What'd you just screw up? Sulfur. Sulfurs, there's 2 here, so what are you going to put here? 2. No biggie. You can fix that. All right? So if you ever have one that's a 2 and a 3, it's not just a multiple of each other, multiply them by their opposite numbers that you see here. All right, let's do this last one together. Actually, I think we can look here. How many silvers? Both sides. 1. 1 and 1. How many nitrates? 1 and 1. How many sodiums? 1 and 1. How many bromines? 1 and 1. If you see no subscripts, except for like the nitrate in this case, then it's all 1 to 1 to 1 to 1. Balancing is really not that hard. You just have to kind of pace yourself through it. So you guys tell me, look on your paper, tell me what what coefficients I need. Shout it out. 2 on the water. So 2. So what else do I need? Anything else?
2 on the H.
2 on the H. Okay, good. Because I needed 2 O's. So I had 2 O's. Had to put it there. Have no other place to put it. That messes up hydrogen. Oh well. Put another 2. Okay. I'm skipping the mercury one. Let's go down to the aqueous iodide. All right. What do I need?
2 by the K on KNO3.
So 2 on the KNO3. Why? Why did I do that?
Because there was 2.
So I had 2 nitrates here, so I needed 2 nitrates here because that 2 distributes over. But now what have I done to potassium? Messed it up. So what do I need?
2.
Where?
The KI.
On the potassium iodide. Okay. Now I've got 2 I's.
You already had
Ha!
2.
Solved my problem, right? So I needed the second I anyway. Ha! It always works out, okay? PB is good too. All right. So balancing masters, thumbs up. I got this. Okay, I got this. All right. So we'll work on that as we go some more. But do not write down these 5 types of reactions. You wrote them down in your reading guide, yes? Okay. We are going to go over synthesis and decomp today, and then probably combustion, mainly because I want to catch something on fire for you. Okay. So we're going to try to go work through the types of reactions. Basically what we're doing is we need to be able to look at a reaction, go, yep, that's synthesis, yep, that's decomp, yep, that's any of the others. So you have to be able to look at them and tell me what kind of reaction it is. You also will need to be able to predict the products of these reactions. So we're going to work on those today, okay? So you're going to want to write down pretty much every example I do today, okay? You want your phones off and you want your periodic table out. All right, so I'll be quiet. I'll let you write down a little bit here, and then we'll do some examples together. And people who do not take the quest yesterday, then you will take it today after school or Monday. Because I don't think you want to skip today's class. I'll let you write down the 2 types of syntheses as well.
If you walked in late, I took up reading out 11 in the test corrections. Yeah, I'm gonna do one thing.
All right, I promise I'll scroll back down. Let me scroll back up first. Okay, so synthesis. Anytime, where have you heard synthesis before in biology? Photosynthesis. What is photosynthesis? Making what? That's not the purpose, actually. That's a byproduct. That's just by accident. Thank the Lord, right? No. Food. Glucose. Photosynthesis makes glucose. Cellular respiration makes energy, right? It's a form of energy, but it's not actual energy yet, right? So, photosynthesis is the purpose of that is to make food. Make. So synthesis literally means to make, to force two things together, to bring things together. So generally, we will have two different reactants being forced together into one product. That's generally what these reactions look like. There are a couple that are a little out of the general form, but we'll do an example of that, okay? So it has one product. That's how you can look at a reaction and tell me it's synthesis. But most of the time when these two things come together, generally they're going to be metals and non-metals coming together. What kind of products is that going to form? What type of bond? Ionic. And if you say ionic, then you're thinking ions, and if you think ions, you think charges. So you have to go back and crisscross the charges. So for example, if I give you barium metal plus, give me a diatomic. Okay, I can do nitrogen, yeah. N2 nitrogen. That says solid. Big lie. Sorry, most of the time non-metals are gases. I just caught that, and I've done this for like 4 years now. Great. Okay, so that's gas. Sorry. Okay, so barium solid plus nitrogen gas. What you have to do in your head is go over to the product side and go, all right, barium's going to be the cation, right? What's barium's charge? Look at your periodic table. 2 plus, right? Cation, right? Plus 1. So nitrogen's going to be your anion, because remember, you always put the metal in the front, non-metal in the back. Nitrogen is going to be a what charge? 3 minus, because it's 3 away from noble gas. Okay, so in your head, you're doing this, and you're crisscrossing. So what is the product that is made? Ba3N2. Okay, it's not as simple as like just smack them together and call it a day. You've got to smack them together and crisscross. All right, so you already know that. You know how to crisscross. That's no news to you. Balance this for me. What do I need for each of these coefficients? 3 on the barium. Is that it? Yep, we're good as gold here. And this is most likely a solid, most likely. Okay, so the other type of synthesis is making a metal hydroxide. So to make a metal hydroxide, you have to have a metal involved, you have to have something with oxygen in it, and you have to have something with hydrogen in it, right? So generally that means that we're having water involved, because water is the best of both worlds. It's got water, it's got H's and O's in it. So the metal oxide though, metal oxides, they're already an ionic compound, because metal, that's metal and a non-metal, right? Because an oxide is a non-metal, metal. So give me an example of a metal oxide. Any metal. Potassium. So potassium oxide. I don't get to just put KO. What is the formula for potassium oxide? So potassium is a what charge? 1 plus. Oxygen is a 2 minus. So what's the formula for potassium oxide? Oops, sorry, there's more marker out. I'm trying to move this down. Okay, it is K2O, because you crisscross those charges, plus water, okay? I know this does not look like it's a synthesis reaction, but it is, okay? And I'm going to show you. I like to write water in a different way. I like to write it like this, because this is literally what it's made up of. An H plus and an OH minus. What's that OH minus called? Hydroxide. So guess what? When this forms with water, which is literally H with a hydroxide with it, the metal and the hydroxide merge together to make metal hydroxide. So what's the metal hydroxide's formula for this one? Okay. Tell me the ion charges again. K1 plus OH 1 minus. Okay. So this is KOH. All right. So then you're going, okay, scratching your head. You're like, okay, I got the K taken care of. I've got this little OH that kind of got mushed. What's left over? We just have these two things left, right? And another potassium to take care of, right? So we've just got an OH to take care of. So that's literally hydroxide again. An O and H together come together to make hydroxide. So that's why this makes sense. Because you've got this OH taken care of, you've got one of these K's taken care of, then you got to deal with this H and O, O and H, which you can just make another one, but you can't add a subscript. What do you want to add in the front here? A 2, because that takes care of the other potassium as well. So that's why it's synthesis, because it looks like you should be doing something more, but they just kind of combine together and you make 2 of them. Okay, so that's a solid as well. This is liquid water. This is most likely a solid ionic compound. So if you ever see metal oxide and water, that's going to be synthesis. And if you ever see a thing plus another thing to make ionic, that's synthesis. All right, so I'm going to show you a modified synthesis after we do a couple practice problems. These are just pictures. Ooh, ah. Ooh, ah. Okay. So, hydrogen plus chlorine. You guys can tell me these quickly. I'll do these with you. Hydrogen, shout it out.
H.
What?
H.
H2. Thank you. H2 gas plus chlorine.
Cl2.
Cl2. Why are we saying these twos again?
Because they're part of the substance.
Right. They're the big 7 and hydrogen. Okay. The big 7 is N2O2 and Cl2 and down. I mean fluorine, F2 and down. Okay. So what do you think they're going to yield, synthesis people? Huh? 2, so 2 is a coefficient, HCl. So what you did in your head was you said H and Cl come together, and then in your head as well, you're like, oh, H has a 1+ charge, chlorine has a 1- charge, makes HCl. That's what you did in your head, yeah? Okay, and you went ahead and balanced because you had 2 of them, so you needed 2 of those. Coolio. All right, magnesium plus oxygen. Shout it out. Mg O2, good job. Now it's not just smush it together and call it a day. What are you doing in your head? Charges and crisscrossing. So in your head, what's magnesium's charge? 2+. What's oxygen's charge? 2-. What do we get when we put them together? MgO. Yeah. We gotta balance it now. So let's balance. What do you want to put right here? A big 2 in the front. So then now you've got 2 oxygens and 2 magnesiums. 2 Mgs in the front. Right. So you balance after you've kind of gotten rid of, you've dealt with your new formulas that are forming. Barium oxide plus water. Barium oxide. In your head, you're going Ba, what charge? 2+ oxygen. 2-. And if you still got to write that out, by all means, please do that, because I don't want you to get a question wrong because you're trying to do everything in your head, okay? Look at your periodic table, get the charges, crisscross them. So barium oxide, because the 2's reduced down to 1, plus water. And I'm just writing it HOH, okay? What does it form? Memorize. Think about what we just did for synthesis. All right, so you're saying BaOH, so you're saying metal hydroxide, right? The metal, though, the metal has a what charge? 2+. The hydroxide has a what charge? 1-. So what's truly the formula for that product? BaOH2. Right. So metal hydroxides can have some subscripts involved due to the fact that the metal has a charge of greater than 1. So you're just doing ionics, uncross them, recross them, uncross them, recross them with something else, another partner. Is this balanced? Yeah, it is, because we have a hydroxide and one hydroxide, but then you have an O and H, and there's an O and H right there as well. There's a second OH. Barium, you got one of, you're good. All right, last one, zinc plus iodine. Zinc plus iodine. Zinc solid plus I2, good, because it's part of your diatomics. Okay, so you're synthesizing, right? So you're making ionic solids. What's the formula for that ionic solid? What's just charge of zinc? Zn is a 2+, because that's one you have to memorize. It's not on the periodic table, it's in the D block, so it doesn't have a specific charge. I'm sorry, it doesn't have variable charges like most transitionals, so that's a specific charge. So Zn is a 2+, iodine is a 1 minus, put it together. I2 as the 2 plus got crisscrossed over. Not because you smush them together. That 2 is not, this 2 is not this 2. This 2 is because I'm diatomic iodine. This 2 is because zinc has a charge of 2. So it looks like you just smush them together, but there's a method behind the madness, right? Okay, so take a minute or two and work with a buddy on these. Do as many as you can. And I forgot, I printed you guys some of these, the ones that we just did. So we'll pass these out as you guys are working. The next example you can write.
In your head, you can remember it. As it's set,
Pardon the interruption. Please enter recycling bins outside the doors. Thank you.
But you're good. I'll give it back to you soon.
don't write the charges, think about them. You need 3 on the other side. They all have 3 plus charge, right?
There you go. And then balance what you want. 2 AL, so 2 in the front and 3 sulfurs. Alright, I'm going to scroll down a little bit and see, or actually I'm just going to expand this. I'm going to do the first one just to make sure we're on the right track, okay? If you're ready, then watch. If not, then don't. Aluminum is a solid metal. It does not say aluminum ion. It says simply aluminum. So you write Al, solid. Then it says it reacts with sulfur. Just straight up sulfur, not sulfide ion, not S2 minus. It's just straight sulfur. And sulfur is probably a gas. It could be a solid. Sulfur is a weird one, okay? Those come together in a synthesis reaction. They come together to form an ionic solid. That is when you find their charges. So you said aluminum has a 3 plus charge, sulfur has a 2 minus charge, leaving us with Al2S3 when you crisscross their charges. So you have to do that after you see what the product is going to be, crisscross their charges. 2 goes in front of aluminum to balance it out, 3 goes in front of sulfur to balance it out. Okay? So notice I didn't put ions anywhere. The ions were in my head, so I could crisscross. Next one, what'd you guys do? Li2O solid plus H2O, which I'm just writing as HOH because I like it, yields. Okay, so LiOH, no subscripts. Why? They both have a 1 plus 1 minus charge, right? So then to balance this out with a 2 Li, you just needed a 2 in the front of Li, lithium hydroxide. Cool, cool? All right, I'm going to scroll down. You guys can finish this up for a minute.
You guys have your student packet? Your student packet? Your student packet.
No, that's just for you. Guys, good questions, okay? Copper 2. This 2 here is for me to tell you when you get to the product side what charge copper is. Because if I just say copper, nobody knows what copper is, okay? This is for your knowledge. It's not for you to write. Not yet. So you simply write copper. That's it. And it's a solid. It's a metal. Oops. Plus, reacts with phosphorus. What's phosphorus? P. Okay. Gas. All right, so when you go over here and you make your ionic solid, you have to know copper's charge. So that's why I wrote it here so you would know it. Okay, so crisscross your charges, what do you get? Cu3P2, because that's how copper's charge is a 2, phosphorus is charge is a 3, crisscross, we're good. Balance? 3 and 2, good. So nomenclature is going to kick your butt until you get it here, right? All right, last one, chromium 2 oxide. Give me the formula. CR what? Oh, okay. Plus H2O or HOH, either way you want to write it, yields.
CR parentheses OH parentheses.
Okay, so this was CR2 plus, this was O2 minus, crisscross. They go to CR2O2. We know empirical formulas now. We know reduced to lowest ratio. Water is water, yields a metal hydroxide. The metal is chromium 2. So you have to crisscross its charge over. Any balancing needed? How many O's are here? 2 on both sides, right? How many H's are here? 2 on both sides. We're hunky-dory. Okay? Let's go to the back. I want to show you a demo. Now, you have to give me some space because I have to explain some stuff. And I'm going to turn the gas. Can I turn the gas on right now? No, I'll turn it on. All right, so stand over, stretch, come to me. You can make 16 strips around here. Let's talk about hot. So, move the forward. This is calcium metal, okay? Calcium metal actually is similar to calcium oxide, but it's just a Ca, no carbs at all. So what we need to do is we need to add some water. This is kind of like the calcium oxide plus water yields calcium hydroxide. But there's going to be one more thing for me here. This is simply just a little bit different of a reaction. So I'm going to attach that something. Hence why I have a balloon, okay? So, you see
see it's forming what? Bubbles. Okay. We're going to see what these bubbles are momentarily. Alright, so you guys back out. Stand up, people. Bring that thing up. Alright, so it's going to be getting some gas in here. It's making some pressure and flowing the balloon up. It's getting really hot as well, indicating what? Chemical reaction. I'll walk behind it. This is my shield to shield your rubber faces. Okay? So we're going to see what happens here. It's almost done reacting. So it's making white stuff in the bottom, okay? That's calcium hydroxide. Does anybody know that hydroxides are basic? Have you ever heard that? So acids are obviously acidic, right? H pluses are acidic. What pH would that be? Acidic. 1, close to 1. So below 7, yeah. So if something is basic, it's above 7. Close to 14? Remember the pH scale from 0 to 14? Okay, so if I tested this, this would be like a 12 or 13 pH, and I'll show you that in a second, okay? I'm going to go ahead and do this reaction. So, probably show the part to show, but I'm not. Let me light my candle. Alright. Okay, so what was in there? What kind of gas?
Explosive.
Okay, yeah. Think about what chemicals, you guys are smart. Chemicals I put in here. Calcium? No. I put calcium and water, and that's it. What had to have been there? I already told you there was calcium hydroxide that was the white solid. Huh? Hydrogen gas, people, that's like explosive, okay? It's also like a billowy, flamey, smoky kind of fire that it makes, so it's some smoking in here. Smoke in there. So it also makes it a disaster. So I just didn't want to get calcium hydroxide on because this is real basic, right? So we can't have that. So how can I prove to you? Oh, that's probably what it's called. I'm a wuss. I know. But I'm going to prove to you that this is basic. We have chemical indicators. Chemical indicators that help us see the acidity or acidity of a substance, okay? When I have phenolphthalein, phenolphthalein is clear. When you put it in acid, it's clear. When you put it in base, it's magenta, pink. So, right, so, I'm expecting color change, yes? So, that's still telling you it's basic, pH 13. Okay? So, yay, science! Back to our desk, let's do some more. We'll come back and do another one in about 10 minutes. Yay, science! I should have played more having gas. It's usually really, really loud and quite scary. Quite scary. Okay, decomposition is the longest slide today, okay? Decomposition reactions, I will be quiet and let you write down a couple things while I turn the gas on. Like I said, talkie, get up. Talkie, get up. Talkie, walkie, talkie, walkie. I will scroll down and get to that quick. Hopefully you're ready. Got to go down? Mark, slow down for me. Take it, darling. Slow down to both of them. Yeah, that's good. I'm trying to get you guys to answer right before I yap at you.
So as you can see, there's lots of types of reactions that we have to be pretty familiar with. So I'm giving you the general forms for all of them, and then we'll do some examples. Scroll up. I just have to So you're seeing all these polyatomic ions, right? And you're just visualizing them. Or if you can't visualize them, you should have your polyatomic ion little cheat sheet out until you still are, mastering them. I still see people take the nomenclature quiz, okay? Make sure you come here, because I want you to have 100 for that before report cards come out mid-April. Oakley dokley, I'll come right back down here. So, starting off, noticing, what do you notice in comparison to synthesis for this type of reaction?
They're breaking apart.
They're breaking apart. So we have synthesis, two things come together. Decomposition kind of makes sense. Things are breaking apart. So we have usually one reactant breaking into 1, 2, or 3 different things. They break apart not simply just by splitting in half and going 2 separate ways. They break apart in very, very specific ways. Generally, 2 things that you'll notice. We usually always require energy for decomposition because this thing is bound together pretty strongly. AB, they're bound together. You're going to take some energy to karate chop that thing apart, to break it apart. So that's why I have a big delta or a triangle here to show you heat is required. Or you also see that gas is evolved. That's very common to see gas evolved. So you guys are going to be doing a chemical reaction where you have gas evolved. You might have to capture that gas. You might have to test for that gas. You might have to do something with that gas to prove the type of gas that's formed. So like we just did, we did a hydrogen test to show that it was flammable because hydrogen gas is flammable because it caught on fire, right? So this one's easy. So I'll give you a quick couple of examples from some of these. Sodium chloride is a great metal-nonmetal ionic substance. Break that apart. Sodium is the metal. Does sodium have any subscript needed? It's just sodium metal. Yay or nay? No, it's just a 1. That's sodium metal. What's the non-metal that's formed? Chlorine what? Gas. So how do you write that? Cl2. So there's our diatomics again. So we have to write Cl2 because that's how chlorine exists in its natural state. How do I balance this?
2 over Na and 2 over B.
Good, because I needed 2 chlorine, so I had to put it in the front on the reactant side, and I had to go back and balance my sodium from the reactant side. Yeah.
How do you just Cl2?
Because you have to know your 7 diatomics from the periodic table. Okay, so guys, tell me the 7 diatomics here. What are you starting with? Nitrogen, oxygen, chlorine, bromine, iodine, and then hydrogen. Those are, anytime they're written all by their lonesome, they're not. They're diatomic. All right, so metal carbonates. So metal carbonates. I'm gonna stick with sodium here, okay? So tell me the formula for sodium carbonate. Na. CO3 is that's the polyatomic, but what's the charge for this polyatomic? 2 minus, what's the charge for sodium? 1 plus, so there's a 2 here when you crisscross. So polyatomics, you gotta know the charges because you have to be able to crisscross them appropriately for your first initial reactant. This is going to decompose into the metal oxide. So what's the metal? Sodium. So sodium has a what charge? 1 plus. Oxygen has a 2 minus. So what's the formula for sodium oxide? Na2O. So in your head, every single time you are crisscrossing metals and nonmetals, okay? Plus, all right, that's just covalent, right? Name that. Carbon dioxide. So just plus carbon dioxide. So what's happening is literally this polyatomic carbonate, it's breaking down. It's breaking down into an O and a CO. Sorry, an O and a CO2. So the O gets stuck with the metal, and the carbon dioxide gets split off because it's a gas. It's a gas, and it kind of evaporates off and goes and does its thing. So this one's very specific. Carbonates make carbon dioxide. Balance this. It's balanced already, right? Because you got C, 3 O's on this side, because 1 plus 2 is 3. 3 O's on this side, 2 sodiums on this side, 2 sodiums on this side. Already balanced, baby. All right, let's keep going. What do you notice about this one? It's reverse of the synthesis of the hydroxides. Look at your synthesis one. What was it? Metal oxide plus water yields metal hydroxide. So we just simply flipped it on this one. So hey, if you get that synthesis one, you got this one. You just got to reverse it. So reverse. Okay. So metal hydroxides break back down into the 2 components that made it up previously. So let's do sodium hydroxide. Let's do that. Sodium hydroxide formula. Sodium hydroxide NaOH yields Na2O. How are you getting the 2? Oxygen crisscrossing, right? Plus water. All right, do I need a balance? Yes. What do I need? 2 in front of sodium hydroxide because you could already see I had 2 sodium, so I definitely had to put a 2 there. And then I can see that the 2 oxygens and 2 hydrogens are now taken care of because I have summative of 2 there and summative of 2 there. So it kind of takes care of itself after you start the balance. Yeah. You got it? Okay. Last one, metal chlorate. Chlorate, a ClO3, what charge? 1 minus. If you don't know the charge, guess 1. I would say 70% of them are 1 charge. Okay. So metal chloride, chlorate. Let's just do sodium again. Sodium chlorate formula. Any charges to be had? Nope. 1 and 1, crisscross, nothing. Yields what? NaCl, sodium chloride, and oxygen. I have to recycle that. Okay. So plus oxygen gas. Balance that baby. What do you notice? So what do you need to do? All right, good. You guys with me? With me? Okay. You notice there's 2 oxygens there, 3 oxygens there. The only way to balance it is to put the opposite number on the other one, yeah? So put a 2 here and a 3 here. Oxygens are balanced, but what have we just messed up?
The NaCl.
The NaCl, because I've got 2 sodiums and 2 chlorines here, so what do I put here? 2. Whew. We are masters, people. Masters. So I just have some images to show you kind of what's happening. Here's the binary one breaking down to the 2 components. That's diatomic chlorine. You can see this one down here is this one's a carbonate here, and it's breaking down into, what's this gas? Carbonates break down to form carbon dioxide gas, and that's kind of what that little molecular structure looks like when we built them in the lab, okay? So let's do some more practice. You guys start these. These, I think I have written down for you on the printed sheet. Just FYI. I tried. I passed it out too late for some reason.
person next to you? There are 3 of them. You should be writing on your paper.
CO2, sodium, oxygen.
The first one is almost correct. What's the carbonate charge? So it's sodium charge. And oxygen, so wait, oxygen has a 2 minus as well. Oxygen has a 2 minus. Remember? So sodium is a 1 plus. Oxygen is a 2 minus. So you have to get the formulas right before you start out. Yeah. Who's calling? Yeah. Who's calling? Oh, I'm sorry. No? Did you forget to crisscross your charges? Crisscross, crisscross. We're gonna make up a dance or something. Make sure you guys remember that. Yeah. Decompose it. Think of the 2 parts that make it up. It's binary. No. H2. It's just the 2 gases. The 2 gases that make it up. Because they're all nonmetals. Yeah. Hold on, I'll do it in a second. Alright, potassium chlorate formula. Potassium chlorate. KClO3, good. ClO3 is chlorate, potassium is a 1 plus charge, chlorate has a 1 minus charge. Decomposes to, what do chlorates decompose to? So metal chlorides and oxygen, okay? So the metal chloride in this one is what? The metal chloride is KCl, because that's a K1 plus and a Cl1 minus, so crisscross, you're good. Alright, plus oxygen, there we go. O2, good job, don't forget your diatomics, right? Balance. 2 here and 3 here and a 2 here, good. Because you had 3 oxygens, you had 2, so you had to multiply by their opposites. You had, once you messed up the potassium chloride, you had to add a 2 to the other side as well. Alright, so chlorates make oxygen. Carbonates make what gas? So carbon dioxide. So carbonates make carbon dioxide. That kind of makes sense. Chlorates You're not going to make chlorine gas, people, because chlorine gas is poisonous and it will kill you. We can make oxygen gas, no problem, okay? So think about the more safe way to do it is to make oxygen gas, okay? Water is a tricky one. Water is made up of H and O, and that's it, right? Decomposition commonly will yield gases. What two gases do you think it's going to make? H2 and O2. Okay, like I said, you commonly make gases. You would never, ever, ever break this down in air to H plus and OH minus, because we don't just poof things into ions. If we did, the ions would be hitting us in the face and reacting with our face and making us turn all kinds of colors, okay? Ions are really, really reactive. This is going to be polyliquid water breaking down into two gases, and those are this, balance. Yeah, okay, cool. Let's see what potassium chlorate looks like when we break it down. Break it down. Ready? Back to the back. Now, this one is really cool. Okay, I got this.
Alright, so this one I gotta go towards the cooler core. So I'm going to talk to you and explain to you what's happening as we go. So what I'm going to do is I'm going to decompose. You guys might want to switch on that side. I'm going to stay on this side a little bit more. That's very good on that side. So what I'm going to do is I'm going to decompose potassium chlorate, which is this white substance in here. I'm going to make it molten. What is going to happen when I decompose potassium chlorate? You guys tell me while it's melting. Potassium chlorate makes. Potassium chlorate makes oxygen gas and potassium chloride, right? KClO3 makes KCl and O2. What oxygen? The presence of oxygen generally yields what? Something that's flammable, yeah? Oxygen gas is flammable. So what happens in your body for cellular respiration? What's getting broken down? Oxygen, aerobic respiration makes oxygen. Uses oxygen to make what? Carbon dioxide and ATP. It's using glucose though, right? Okay, so that's what we're going to just die for the sake of education. Okay, so what gas did I just make? Not just one. Sorry, the first gas I made when I was heating up the chlorate. I made oxygen gas, right? Okay, oxygen gas reacts with glucose in your body, C6H12O6, yeah? So oxygen plus C6H12O6, that's the cellular respiration equation. It makes energy, ATP, 36 ATP, water vapor, and carbon dioxide. So if I tested this gas coming out right now, what gas would that probably be? It could be water vapor and carbon dioxide, right? Water vapor because it's really hot. And obviously you can see it makes energy. This energy is not energy you would use in your body. This energy is like hot fire energy, okay? So that's called the death of the gummy bear. But it's actually two reactions in one. The first reaction I did was decomposition. The second one I did was combustion. We'll be reading here in a little bit, okay? So, hey, sorry gummy bear, but thank you for your educational sacrifice. Back to the front.
Educational sacrifice. Did I turn off the gas?
Yes.
Okay. 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 I'll go over this one in a second. All right, let's do some more examples together. Please write these down with me, okay? We have two examples we're gonna do for decomp, and then I'll let you guys practice for a bit more soon. Okay, magnesium chloride formula. Shout it out when you get it. Where'd you get the 2 from? Magnesium's charge. You crisscross over. So this was magnesium 2 plus, chlorine 1 minus. Crisscross, you get magnesium chloride. Decomposes, okay? Because if it doesn't say anything else, you're assuming decomposes. What does a binary substance decompose into? Its 2 parts. What are its 2 parts? Magnesium solid and chlorine, which is Cl2, which is a diatomic gas. So that one literally looks like we chopped it in half and split it up. Sometimes it does look like that. But we know that 2 came from magnesium's charge, and that 2 just means, hey, I'm diatomic. Those two means those twos mean different things. Balanced? Yep. Okay. Calcium hydroxide. Ca. Where are we getting the 2 from? Okay, calcium's charged, hydroxide is a 1 minus charge. All right, think back to the synthesis one we did. Remember, we took 2 things together and we made metal hydroxides? What were those 2 things we put together to make the metal hydroxide? What was one of them? Water was one of them. So remember, this is just the reverse of that synthesis one. So we know water is one of the things that are made because that's what it was used to make. What other thing came with it? Think back to your synthesis. Try not to look at your stuff. Metal oxide. Thank you. So calcium oxide is what the metal is, right? So what we had for synthesis, we had metal oxide plus water yields metal hydroxide. Now we've got metal hydroxide breaks down to metal oxide and water. So what's the metal oxide here formula?
CaO.
CaO. Good. Why no subscripts? Right. They were both reduced down, right? So it was Ca2O2, crisscross down, reduce. Balance?
Yes.
It's already balanced? Yep. 1 calcium, 2 H's, 2 H's, 2 O's, 2 O's. Woo! Okay, we just did the fume hood one. We just did that. Okay. You guys have, I want to wait, make sure you guys are good on this one. Who's got it down? Okay. You guys have, I'm going to skip this for a second. I have a lot more that I might do. You guys have 2 practices I want you to do. This is on the student packet. I don't think I printed it. I'll leave this up here. But this is the synthesis homework. And then I have one, oops, down below. This is the synthesis homework and the decomposition homework, okay? So there's 2 of them. There's only five balanced equations per type of reaction. I did not print this for you. I should have, I'm sorry. So I'm going to leave this up here. So you guys take a little bit and balance and predict the products and balance those. You will want your notes in front of you, okay? So I would say take about 10 minutes right now. You can do it on your notes, that's fine. I'm going to check them on Monday. Come around and look at them and check them. So we'll go over some of these. So this is on the printed packet. I'm going to see if I can squeeze this onto 1 page, so just give me a hot second. It's not on problem set 11, but it's printed on in the same packet.
Can I go to the bathroom?
Mm-hmm. It's like before or after problem set 11. Okay, got you. Thank you. All right, if I put this like this, is this visible enough?
Yes.
Is that good? Okay. Practice makes perfect.